Hi everybody, so in this video I'm going to talk to you about valence electrons and ion prediction. So as you previously have known, you can predict the charges of valence electrons by their position on the periodic table. In fact, you look at these little A numbers above each group and it tells you how many valence electrons it has. So group 1A has 1 valence electron, group 2A has 2, Group 3A has 3, and so on. There is only one exception you need to know, and that is helium, which has 2 valence electrons. Hopefully this makes sense. Valence electrons are on the outside, on the outer energy level of an atom. And if it's on the outer energy level of an atom, right, all of these atoms have more electrons than the number of valence electrons, except for helium. Helium only has 2 electrons total, so it can't have 8 valence electrons. But if you look at all the other atoms, right, Li has 3 electrons total, but it has only 1 on the outside, on the outer energy level. Sulfur has 16 electrons, but 6 of them are on this outer energy level. You know this from doing these Bohr models that we did in class. You can see that this atom on the left, calcium, has 20 electrons, and each energy level has a different number. So the first one has 2, and the following ones have 8. And you can see that the outer energy level has only 2 in it. So that's 2 valence electrons for the fact that calcium is in group 2A. On the right here, we have fluorine. Fluorine has 9 electrons, as you can see from the periodic table, right there. And it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. As you notice, 8 is a special number. 8 is called the octet, and we'll talk about that when we talk about drawing two-dimensional structures called Lewis structures. Atoms are trying to get to 8. Why is 8 so special? Because 8 is the number of valence electrons that noble gases have. And as you remember, noble gases are stable. They don't want to interact with any of the other atoms. They're happy with it the way they are. That means that every other atom is trying to be like a noble gas in its electron configuration, in its electron state. And when it does, it becomes stable too. Notice that fluorine has only 1 open spot remaining. So it wants to get 1 more electron. It needs 1 more to become like the noble gas next to it, which is neon, as you can see here. Neon is right next to fluorine. It gets 1 more electron and it becomes like neon. So when it gains that electron, it becomes F minus, a -1 charge. Where calcium, it would have to gain 6 more, right? And gaining 6 electrons is pretty hard, so it's not going to do that. It would rather lose those 2, lose 2 electrons. And when it loses 2 electrons, it becomes like the previous atom on the periodic table, that's the noble gas, which is argon. And I'll use orange here to label argon. Notice if you take 2 steps back from calcium, it looks like argon. So that means that when calcium loses these 2 electrons, it becomes a positive 2 charge. And you can follow that pattern throughout the periodic table. Over here on the left, we have magnesium. Magnesium has 2 valence electrons, which is in group 2A. It has 12 electrons total. Is it going to gain 6 to become like argon? Or is it going to lose 2 to become like neon? Well, losing 2 is more favorable. So it's going to lose 2. It's going to become the charge Mg2+. Similarly, on the right, we have sulfur. We have sulfur right here. Sulfur has 6 valence electrons because it's in group 6A, 2 there, 2 there, and 2 more, which is 6. It needs to get 2 more electrons to become like argon, or it can lose 6 electrons to become like neon. So which one is it more likely to do to get that full valence shell? It's more likely to gain 2. So when it gains 2 valence electrons, it becomes like argon also, so it becomes an S2-, right? 2 more electrons than protons it has. So I hope you're seeing a pattern. Everything in this group, those atoms become -2 ions. Group 7 becomes -1. This group doesn't become any charge. Group 5A becomes -3, right there. Group 1A becomes +1. Group 2A becomes +2. Group 3A becomes +3. So you notice from the left, the atoms want to lose electrons. Metals like to lose their electrons to become like noble gases. And nonmetals here like to gain electrons to become like noble gases. So basically they're trading with each other. Metals lose their electrons, nonmetals gain their electrons. Now the key is knowing here as well is that carbon is kind of in the middle. It doesn't gain or lose. It's very rare to find a carbon atom in an ionic compound, in a compound that has ions in it, charged atoms. So in this case, you're not really going to be able to predict whether it's going to be +4 or -4, because usually carbon atoms are sharing electrons rather than gaining or losing them. There are exceptions to these rules, but we're not going to worry about them. You just have to memorize this pattern. We're going to ignore all the transition elements that are in the middle. So the pattern is, from the left, group 1A has 1 valence electron, and when it loses 1 electron, it becomes +1. The second group will lose 2 electrons and become +2. The third group will become +3 when it loses 3 electrons. Remember, electrons are negative, so when you lose them, the atom becomes positive. Group 7A will gain 1 electron to become -1. Group 6A will gain 2 electrons to become -2. Again, when you gain something negative, the atom becomes negative. And group 5A becomes -3. Again, you can't really predict group 4 because it usually shares electrons rather than gains or loses electrons. So I hope that's useful, and you'll have this quiz very soon.